This is the MOOCs course on high performance computing for scientists and engineers. We are discussing module 4 on GPU computing and continuing with previous lecture on thread execution in a CUDA program. We have looked about thread scheduling. We will see some more details on thread scheduling and synchronization, and then we will see how memory access is done by different threads in a CUDA program. So, you looked about execution patterns of the thread, and which involves scheduling at the warp level. Warps are collection of 32 threads in the modern GPUs, which are executed at one go in the streaming multiprocessor. So, every time we launch a kernel, it launches blocks of grid threads, and the collection of the blocks of threads is called a grid. Inside grid there are blocks, inside blocks there are threads. Each block of thread goes to one streaming multiprocessor, and there can be more blocks going to one streaming multiprocessor, but one block will as a total will go to one streaming multiprocessor, and the threads inside that blocks will be executed in that particular streaming multiprocessor, and at one go 32 threads among them is chosen, and this number is chosen continuously as per the thread ID, and these 32 threads are called the warps, which are executed at one instance. Once this warp goes to the streaming multiprocessor, 32 cores are allotted from them. They are executed. As soon as they are being executed, during this execution, if they go to some of the encounter some of the latency for searching data or for something else, the next warp is activated, and that starts executing. Once the first warp's latent phase is over, it comes back to the context goes back to that warp, and it is executed again, and in that way multiple warps are executed with some dynamic scheduling within a streaming multiprocessor, and that is how a large number of threads, much more than the number of cores, can be executed in GPU with good scalability. And what we have seen from the from this scheduling aspect is that as one warp is active at one particular instance, therefore, and the block, all the threads of the block will be executed as group of warps, as collection of warps. Therefore, the block size must be a multiple of warp size, and we have seen that there for one particular case there is an particular block size which gives better performance. So, depending on block size, performance also changes because thread scheduling and latency hiding varies. So, it is the optimum block size must be multiple of warp size. If the block size is not a multiple of warp size, there will be serious performance degradation. Also, it depends on, or the optimum of block size also depends on memory access patterns. So, therefore, the same GPU code with changing the grid size, changing the block size and the number of blocks inside the grid, we can get different performances, and there is an optimum performance level. And thread divergence has to be avoided, which tells that threads within a block must not take different execution path. So, let us see what is thread divergence. It is recommended that threads in a particular warp must follow same instruction following an SIMD model. SIMD is single instruction multiple data model. That means they must have the same instruction, and different threads will operate on different data elements, and preferably that should be from a contiguous data set, well, whatever. So, the instruction must be same for all the threads in the warp, and this instruction will be executed in parallel in all of the threads. In case the instruction sets are different, some of the threads are asked to do something, some other threads are asked to do something else, and that can be done through an if-else statement. In case it is there, the first set of tasks will be operated in those threads, in the designated threads. The other threads will be in a latent manner. The cores to which these threads are assigned, they go to an idle phase. This part of execution will be over by the active threads. The next instruction set will be chosen, and the previously active threads, because they are not supposed to do this next set, they will go to in a latent manner. And therefore, if there are two different instruction set by if else statement, half of the threads are active at any point of time. Although warp scheduling tells us 32 threads are active, this is the unit of parallelization in GPU, 32 threads are active at any go. However, if else is given for 16 threads, 16 will be active, therefore performance will fall by at least a factor of 2. Let us see an example that if I is the thread ID, if the remainder by dividing I by 2 is 0, that means it is a thread ID is even, then xi, particular location of the vector x or the memory x, will be 5. If it is odd, then xi will be 10. So, when this will be executed, when the even threads will come, then the odd threads are in a dormant or latent mode, and when the even threads work will be over, then the odd threads will be active, but even threads will go to a latent mode, and this is called thread divergence. This will create two different control paths for threads in a block, and always this is limited within a block. For the other block, that is an independent thing, but the same thing will happen because you are executing same statement in all blocks. Even threads follow different path than odd threads in the warp, but all threads will reach the same instruction. So, there will be a sequentiality of the instruction set. First, all threads will look into this instruction set, and this instruction set, all threads will look into this instruction set, and then all threads will look into this instruction set. When first set of all threads are looking into this instruction set, only these threads are doing this part, but everybody is looking into that. Now, when, because warp is scheduled together, the threads are active together, so everybody is looking into this if, and if it is not so, they are waiting. And when else is done, then everybody will looking into this, and only odd threads will look into that, the others will be waiting. And this is a performance killer. By the programmer himself is doing something which is putting threads into latent mode, putting codes into idle stage, and therefore performance degrades. However, in many cases you cannot avoid if else statements. Some threads will do something, some threads will do something else. To avoid this, you do more computing in each thread, crunch more numbers, because this is faster process, but do not put any thread into latent state by if else statement. So, write that for even there is some calculation, for odd there will be some other calculation. So, you add this, combine this if else statement and modify the program execution accordingly. Here all threads essentially execute the same state instruction, but they do the calculations are different for even and odd. That is not an issue, but none of the threads are waiting or in idle state here. So, that is how thread divergence has to be avoided. In some case it can cause deadlock. Say we write some of the threads, thread ID less than 60 to run some function, and thread ID greater than equal to 16 to run some other function, and put a sync thread in this. What a sync thread does? Sync thread is a synchronization or barrier state. It will not allow the threads to do anything else till all other threads in the block has reached till this point. Now, even threads or threads less than 16 will operate this. Thread greater than equal to 16 will not even come up to here, but the threads less than 16 are waiting here, they cannot do anything else. Therefore, it will go to a deadlock system and the code will stall. Half of the threads in the warp will execute first instruction and wait for the others to finish till sync threads, but others cannot finish that because others are here, cannot operate it till this loop is over. There is a sequentiality in operation due to thread divergence. The next 16 threads cannot start the second task because the second execution path, the else if, has not been activated. Therefore, the code stalls. So, these are something which has to be avoided. That means, if else using thread IDs inside a inside a kernel is a strict no-no. If you do that, your performance will be degraded. However, there are certain cases when you cannot avoid that. When you are writing a complex program, sometimes you cannot avoid using logical statements like if else, but you have to avoid thread divergence. So you should not put this if else statement within the based on the thread IDs within the kernel. Rather, few things you can do at the warp level. You see that if the warp is scheduled to do some work at one go, so instead of odd even branching, say if you club all the threads in the first for thread id less than the warp size in to do something else, thread id greater than warp size to do something else, so two different warps will take two different execution path. That is possible. So instead of doing if else statement in the thread level, do it in the warp level. Diverge at the warp level. Different warps are doing different work, which is possible. You can diverge at the block level. Using block ID, say that some block will operate on something, the other block will take the other execution part. Or you can launch different kernels, identify the work which is, say for even you have to do something, write a kernel, combine them such that all the event threads now become threads of one particular kernel, renumber the threads and rearrange them. So launch different kernels. By these few methods you can avoid thread divergence and improve the performance. Thread divergence kills the performance at least by the factor of the number of divergent different execution paths or if else statements inside the kernel function. Now we have seen earlier thread synchronization. Sometimes it is important to synchronize the threads or put a barrier on the thread activity, because say we can have multiple blocks, there can be some data dependency among the blocks. We can launch multiple kernels. The kernel call is not a synchronized call. Once you call the kernel, control goes back to CPU, it again launches the next kernel, but there can be data dependency among the kernels. Therefore, if you do not synchronize them, especially for case of data dependency, the result can be wrong. So there many times you need to put a barrier, and this sync threads is a synchronization command. It ensures that all the threads in that particular block have completed the phase of that execution. Where you have put sync threads, up to that all the threads in the block have completed that. That means though you are scheduling at warp level, all the warps are activated till all the threads in the block have done till that particular job, and then the control can go to the next step, then the next executions can be started. This adds waiting time as well as latency, because the one warp is finished, the thread readily cannot pick up the next work, or the next kernel cannot be launched. There is a waiting time, but it is important in many cases, especially when there is data dependency from the previous and new execution. However, this waiting time can be reduced if we allocate threads in a block as a unit in a very contiguous manner, that these threads will look into contiguous set of memory, because threads are picking up memory location as a chunk. If the memory and thread allocation and the thread allocation on the work has very close proximity, then all of the threads are doing finishing their job almost at the same time. There is no wait time for one thread for the others. The wait time is anyway less, so even if you put sync threads, they are just synchronizing it, the wait time becomes less. So utilizing proximity of threads both in terms of execution and memory, ordering the threads correctly, pointing them to the right memory in an ordered manner, the synchronization time can be reduced. And some operations like CUDA mem copy, CUDA malloc, when we write these functions, they are implicit synchronization. Though we do not need to write sync threads, these operations will implicitly include a sync thread command. So all the threads will wait till these operations are finished. So they are also synchronization operations. Synchronization works for threads in a particular block only. This is important. that we are launching many blocks, but synchronization is done only within a block. No coordination is possible among different blocks. These blocks run independently. The multiple blocks can be scheduled to a particular streaming multiprocessor, but there is no synchronization among the blocks. At the block level, they are running independently, cannot be synchronized. How the blocks are scheduled? Blocks run as independent units of threads. Blocks are scheduled on streaming multiprocessor based on the availability of the streaming multiprocessor. So there are 80 streaming multiprocessors, but more blocks. 80 will go to 80 different streaming multiprocessor. Then how many cores are available on the streaming multiprocessor? Based on that, more blocks will go to the streaming multiprocessor. Also, how the on-chip memory is available, that is another factor. Block to SM allocation may vary differently during different execution of the same code and in different GPUs also. So same code, how block and streaming multiprocessor mapping will be done, that is kind of arbitrary, and therefore the order of execution of different blocks, first block will be operated maybe at the 7th streaming multiprocessor, 31st block may be at the 5th streaming multiprocessor, and 130th block may go to second streaming multiprocessor at the second go, or it might go another streaming multiprocessor, and there can be random arbitrariness in the operation of the blocks, and this creates an interesting situation that the entire job is being executed by threads, and these threads are going as blocks of threads in different grids, and different group of threads or different blocks are executed in different order because blocks are operated in different order. We do round of error in a calculation. Sometimes the calculation round of error has some impact on the final solution. As the operation of the blocks are different, the piling up of round of error becomes different. Therefore, different execution in the same GPU will have different amount of round of error because the order of execution of the blocks will change during different instance of the same code, and so you will get different results. However, these these differences are only due to round of error, which is less than the machine accuracy or machine precision. So your solutions will be correct to the order of machine precision, but the round of error makes them different. So correct but different solutions you will get at different run of the same code in GPUs, especially when you run at different GPUs also. But all these are correct, only difference is in terms of the round of error, which is anyway part of numerical calculation. So you can see that, say you have a device with 2 streaming multiprocessor, there is a allocation of block. In case you have device with 4 streaming multiprocessor, there will be different allocation of blocks. So the operation will be very different. In case some of this, because multiple kernels can launch on the GPU, some of the streaming multiprocessor is taken by a previous kernel, then you will see a different allocation or different scheduling of block is happening. However, block scheduling, because blocks are populated over all streaming multiprocessor and they are keeping the streaming multiprocessor busy. In case you have blocks more than the streaming multiprocessor number, that does not make a problem, which can create a problem is the thread level scheduling or warp level scheduling, and that is why the block size has to be optimum, which is giving right performance. Now the next important thing is that how memory access is done in GPUs. We can see that we have discussed about registers. Large number of registers are available in GPU cores, and each thread gets memory from the registers, which are on chip memory, which are on the streaming multiprocessor. So it does not need to read the memory from the device RAM, which is a slow process, because it is connected through an interconnect. Reading from device RAM is slower. But if the memory requirement is more than the what is in the register, than what can be supplied by the registers, then the threads read from the local memory, and this is in the device RAM. So a private memory is created for all threads, is created in the device RAM in case it requires more memory than the register, and many times it requires so, and this reading becomes slower. The blocks, threads itself can look into registers and local memory, but the block as a whole can look into shared memory, which is a small memory, 64 kilobyte, 96 kilobyte size of memory attached to the streaming multiprocessor directly. So, it is an on-chip memory, it is a first. So, we are talking about two terms, on-chip and off-chip. Off-chip means which is in the device RAM or GPU RAM, on-chip means which, and the GPU RAM is connected via interconnect to the streaming multiprocessors, but on-chip means which are directly on the streaming multiprocessors and can be read much faster. So, off-chip memory has a slower access, smaller bandwidth, on-chip memory has first higher bandwidth and fast access. And the kernel, when the kernel is launched, the kernel communicates with the global memory. So, whatever we are copying from the CPU memory is copying into the global memory, and the kernel reads from the global memory. This is usually uncached, but now from kernel to thread level we can see there are L1 and L2 caches in modern GPUs, and kernel can read and write to the global memory, etc. So, we can see that the global memory and local memory, they are from the device RAM. So, accessing global memory and local memory are slower compared to shared memory or register access. These accesses are faster, but these are small memory units, especially global memory is a large memory unit. When a CUDA kernel accesses a data region in the global memory repeatedly during, say, it is doing a matrix multiplication, so many times it needs to access elements of the column, then this access is called a persisting access. Many times during the kernel execution that memory is being accessed. On the other hand, if the data is accessed only once and then this data comes and is loaded in the registers and it works, it is considered to be a streaming access. Persisting access requires many access with the global memory and is a slower process, adds more latency. DRAM or global memory is connected to the SAMs through interconnect switches, not switches, through interconnect memory interconnects, and hence memory transfer from the DRAM has slower bandwidth and higher latency. So, persisting access is costly. Different level of caches are used in GPUs. However, the cache size for each streaming multiprocessor cache is not big, is of kilobytes, hundreds, few kilobytes. So, we can see that because we have a persisting memory access which is costly from GPU memory. So, this is the CPU memory which copies to GPU memory. From GPU memory to streaming multiprocessor there are L2 and L1 cache. These caches are not large caches, small cache sizes, but with development of modern GPUs the cache sizes are increasing. Starting with CUDA 11.0, devices of compute capability 8.0 and above have the capability to influence persistence of data in L2 cache, providing higher bandwidth. So, persisting use, one is that making different cache for persisting and streaming memory and provide more spaces for persisting memory, as well as from compute capability 8, data is fetched and put into the, especially the persisting data is fetched and put into the L2 cache so that the read is faster, and this adds to the less latency and access to global memory. So, one important issue also comes here, that is cache friendly programming, because data will be now pulled from the GPU memory and put into the L2 cache. Earlier we had an idea, especially for the older version of GPUs, there is very less amount of cache available, but now as L2 cache and especially for persisting data there is sufficiently large L2 cache. Cache friendly programming is important so that data can be prefetched and resides in the cache, and as soon as the streaming multiprocessors are accessing the data, it can directly look into the cached data. So, the bandwidth is not lost. And one important, because global memory reads are slower, one important part is compute to global memory access or CGMA, that is how much calculations you are doing for each access to global memory. How many calculations are done for each access to global memory. If you are loading many global memory data and doing small calculation, then CGMA value is small. If CGMA ratio should be higher for good performance. If CGMA ratio is 1, that means for one operation we are doing one memory access. Now memory access is always slow, so the computing speed is being limited by the memory access speed. So you should try to have higher CGMA access compared to global memory access, that for one global memory access more computing is being done. So the because due to this CGMA, which can get sometime close to 1, even small, we do not get the theoretical peak performance, because theoretical peak performance is based on how many floating point operations the core can do. But now if you have one memory access per floating point operation, then your speed is limited by the floating point operation and the speed reduces in that respect. For better performance, more calculation should be done compared to global memory access, and cache friendly codes are better performing. A very important performance consideration for programming CUDA capable GPU architecture is the coalescing of global memory access. Why? If you coalesce, instead of a 2D array, if you put into a 1D contiguous array, coalesce the global memory. When the warp reads the memory, once memory element is read, the entire 32 threads requirement is coalesced and put into the cache. So all the threads can readily read the memory, and the memory access time reduces. The cache can be used efficiently. So coalesced memory access is an important aspect. Say if you are accessing memory, each thread is accessing a memory which directly points to the memory location, which is good. So each 32 threads can go and utilize the entire bandwidth, fetch the 32 memory element data and can read it. But there can be offsets, one thread may need more memory elements. In case there is a misaligned but an offsetted issue, one thread when it is reading, it is fetching some data in the cache. So in case there is a regular access, the cache is helping to fetch the next elements of the data, and effectively it is getting the same bandwidth. In case the access is not regular, then the there is a cache miss, and therefore many times it has to access global memory, and based on the CGMA value, the performance will fall down. So the first case gives highest bandwidth, the entire bandwidth can be used, 32 data can be read and accessed. In the second case, though there is a misalignment, but whatever is read here, the next data is always sitting in the cache, so it can read from the offset value is accommodated by the cache. So effectively the bandwidth is same, though it requires some offsetted data, but that is already residing in the cache, it can utilize the cache memory. In the third case, we can see that with increase in the stride size, the first thread requires first data in first location, second thread requires data in second location. In third location, in case we have more stride size, we need more offsetted data, the performance can degrade heavily. We can see that if data access is of this pattern, performance can fall down, and we may get even worse performance than CPUs, because memory access due to smaller cache, memory access is slower here. In CPU you have large cache, so even if you are using striding memory access, entire data is sitting in the cache and getting better speed. Now these are the few memory units: register, local, shared, global, constant, texture. You can see from the name texture, it is more related with the graphics processing, because GPUs are graphics processing unit, the names has some legacy of their original use. The register and local memory, they are assigned to the threads, they are read write memories. Local is cached memory, register is not cached, then this is a very small amount of memory, you do not need to cache it. The local is an off chip memory, so it is a slower memory, register is on chip, faster. Shared memory is an on chip memory which is not cached, which is a small memory, but all threads in the block can look into the shared memory. See, even one warp writes something in the shared memory that will reside in the share in there, and all the threads can utilize that. Global is the main off chip memory, which is now cached in L1 and L2 memory, earlier it was not cached, and these all are read write memory. There are some read only memory which are constant and texture, and they are off chip, but these memories can be very fast read by the streaming multiprocessor. There are some hardware benefits there. Let us look into it detail. Constant memory is 64 kilobyte memory on the device. This space is cached, and constant cache is best when threads in the same warp accesses only at few distinct locations. If all threads in the warps access the same location, this constant can be as fast as register access. So though it is in the off chip, but it can be very fast if it's constant. If it has a constant value, all the warps are trying to threads in the warps are trying to read the same memory, it can be done very fast. Texture is a read only memory, constant and texture both are read only memory. In certain situations like say it can be especially certain addressing situations, so reading device memory through texture fetching can be advantageous, then reading device memory through global and constant memory. Some filtering aspects special mostly for graphics purpose, we will not discuss here the texture memory from scientific computing perspective. Local is named because this is local, this is like a private memory to the thread, and this doesn't in physically it is not local memory, physically it is not sitting close to the thread, it is sitting in the device close to the global memory. It is off chip and it's an expensive memory as global memory, but if a thread requires some memory private to it which is more than the register memory, then it takes from the local memory which is in the device itself, in the device RAM itself, and it is a slow memory. Local memory is used only to hold automatic variables, the variables which has the scope of the thread, does not alive after the thread is over, and this is done by NVCC compiler. It compiler determines if there is sufficient space in the register to hold the variable, if not then these are placed in the local memory. So we should also try to put these automatic or private variables small for each thread so that local memory is not much required, because local memory is a slower memory, its access will degrade the performance. Shared memory is an important memory. This memory is shared by all threads in the block. This is the memory on the sitting on the streaming multiprocessor. So its size is typically 64 to 96 kilobyte. In V100, 96 kilobyte is total given, and it can be configured for both, I mean part of it will be shared and part of it will be L1. It has to be shared, I mean shared memory space is shared by shared and L1 memory cache. However, because this is an on-chip memory, it has much higher bandwidth and lower latency than the local and global memory. So if we can put, if one, and this has the scope of the block, once the block is active, the shared memory, its threads can read the shared memory space. If one warp can fetch data from global memory and put it into the shared memory, and the all threads in the blocks are okay with that shared memory, then only with that read the memory resides in the shared memory location, and the next warps can utilize this memory and can be a very fast process. Shared memory is allocated in the per thread block, so all threads in the block have access to the same shared memory. Threads can access shared memory loaded from global memory by other threads within the same thread block. So once it is loaded in the shared memory, it resides till the block is active and the threads can operate over there. And in many cases we can see we can get optimized performance if we can use the shared memory, but its size is small, the maximum size is 96 kilobyte. So the total size memory requirement has also to be reduced for this activity. However, as different threads can try to access the same memory location in shared memory, there can be race conditions leading to errors in calculation. Therefore, if there especially there is data dependency, as it is available to the whole block, one warp is over and the next warp is launched, which is taking care of the next part of the execution, and they are trying to look into the same data. However, some data is still not being written, and therefore there can be a race condition among the threads. Therefore, sync thread is must, especially if you have data dependency in a shared memory. So say you see the example that st, you are reading something in shared memory and wrote st is equal to dt, and you will change the memory locations, dt will be str, t is the thread id. So you put a sync threads here that all the threads will finish up to this part and then this next will go, and the shared memory has to be declared as shared in the kernel itself. If we looked into a Jacobi solver for matrix solutions, and we can see that when the matrix size is small, shared and without shared performance is similar. Actually, without using shared memory, performance is better because matrix size is small, so everything is fitting in the cache and only read from cache is sufficient enough. But for larger matrices, when we are using a Jacobi solver, at least 15-20% improvement in speed happens when we use shared memory, because now entire matrix cannot fit in cache. So you fetch the data required by the block and put it into the shared memory, and the one warp will do that, and the other warps can work on that, other threads can utilize that and operate fast. To achieve high bandwidth, shared memory is divided into equally sized memory modulus called banks, which can be accessed simultaneously. So shared memory has many equally sized memory modules or banks, and each thread can directly access a bank and read from there. If there are in the warp there are 32 threads, so at a go they can read 32 bank locations and fetch memory from there. This increases the latency. There is no sequentiality in memory reading among the threads, or also there is no race condition in memory reading because 32 locations are directly read by 32 threads. But now programmer has to be smart enough so that each thread looks into a particular bank. Many threads do not look into the same bank. Number of threads do not look into the same bank. There is no bank conflict. Any memory read or write request made to n addresses that fall in n distinct memory banks therefore can be serviced simultaneously, yielding an overall bandwidth which is n times faster than a single module. But now, if multiple addresses of memory request map to the same memory bank, the accesses are serialized. If many threads try to read from the same memory bank, now this will be serialized. One thread can look into one memory bank. If many threads are looking into same memory bank, this will be serialized. Hardware splits memory requests that has blank conflicts into many separate conflict-free requests as necessary, and therefore effective bandwidth reduces. And we can see that this has no bank conflict. So all the 16 threads here, this is a previous GPU where there are 16 threads per warp, now there are 32 threads, but all the 16 threads are readily reading from this memory, so the effective bandwidth is actually 16 times more. However, reverse condition happens here, that all the 7-8 threads read from the same bank. So one by one the threads are reading there, effective bandwidth is reduced by 8 threads here. So it should not be done. Threads should look into distinct memory locations so that bank conflict is avoided. They should not look into, many threads should not look into the same memory location, especially when using shared memory. This has to be taken care of by whom? Programmer will take care of that how threads are accessing the memory. In case many threads are trying to read, modify, write in the same variable, which is often done. One variable is being updated by many threads, and this is done through atomic operation. Atomic add reads a word at some address in a global or shared memory, adds a number to it, and writes the results back to the same address. This avoids race condition and contentions. We have looked into atomic, many threads trying to modify the same memory element. So instead, in order to avoid conflict, they are done in an atomic way. So there is a sequentiality among the threads, each thread one by one writing to that memory location. And you can see this atomic add system, where this address, each thread comes and adds 10 with this atomic add. And after atomic add, after the kernel is activated, there is a synchronization which says that this atomic add has been done correctly. The other operations are atomic sub, atomic mean, atomic max, etc. However, this operation is essentially serialized and they can degrade parallel performance for large block sizes. So when we are doing atomic operations, this can avoid race condition, can give us right results, but we have to be careful while doing so. Well, so these are the references I have used. We looked into, in last 2 lectures, we looked into thread scheduling in forms of warps. Threads are scheduled as a group of threads within a block runs in the streaming multiprocessor, and this group is called warp, which size is 32. warp divergence or thread divergence reduces the performance. We have looked into that. Memory access issues during GPU thread execution is seen. It is seen that shared memory, especially for large problems, if we can break down into smaller blocks and utilize shared memory efficiently, then performance improvement is there. And shared memory is accessed in banks. While accessing shared memory, bank conflict has to be avoided. Well, so in next class we will look into matrix operations, and well, we will move forward with the concepts which we have discussed till now. Thank you.